This is about circles and some terminology and how things work. First we're going to talk about what it means to be round. Circles are round. I'm going to take two equal sticks here, make them chords to kind of slice off a portion of the circle. Okay. I'm going to do it like that. As I do that, it'll create a portion that's cut off that'll be somewhere along like this. Okay, there's one slice, a circle. And there's another slice of circle. Since the two slicers, the two green sticks, are the same, it sliced the corner. We say, well, how do you know that? Well, think about it. This is just kind of thinking in general how stuff works. Say, for example, you had a grapefruit, and you have a 4-inch paring knife, and you're going to slice off just exactly how much will work, so the knife is just exactly how much it takes to cut it. You slice off someplace on it, if it's exactly a sphere. You slice it off, you get a chunk of grapefruit. Then any other place on there that you hadn't already cut, you cut it again exactly so that it's a 4-inch slice with your paring knife. You get another chunk. Guess what? It's the same chunk. Now you know that. You've sliced up fruit. It's going to work that way. You use the same size of cut, 4-inch paring knife, same size of cut. You're going to get the same chunk of grapefruit. Why is that? Well, it's because it's round, assuming it's actually a sphere. We'll assume that. Okay, so it's round. That means that the curvature is always the same. It's always the same all the way around. So wherever you choose to slice it off, when you slice off a 4-inch hunk of the grapefruit with your paring knife, you're going to get the same amount of grapefruit as you are if you slice it someplace else. That's just what it means to be round. Okay, well, let's contrast that with not round. So here we'll have a figure that's not round. It's a trapezoid. What's going to happen when we do the same thing to that? I will take my two green sticks and I'll make one slice right about like that. Okay, so that'll look about like that. So there's my chunk of trapezoid, sliced off with the same size, and then I'll take a chunk down here and slice it off. Same knife cut, different kind of a weird kind of shape of fruit, but if you would take your same 4-inch paring knife, make two cuts that exactly fit, you don't get the same amount. It might be possible to rigor out a way with this trapezoidal fruit to make it so that it was the same, but you're going to have to figure on it. You just can't go any place you want and get the same amount of orange sliced off. Most of the time it's not going to be. Okay? Think about why not. Well, it's because it's not round. Because the curvature or the shape is not always the same every place, no matter what you pick. So it's not going to work. You're going to get a different slice. So unlike the circle that is, round, any place you slice it, you're going to get the same amount. Here, you're not. It might be, it might not. It'll be kind of weird that way. Okay, let's look a little bit more here at the circle, since circles is what we're doing. If I take this circle and I make sure that my cuts are the same, I'll say that they're 4 3/4 inches, approximately 3 3/4 inches, 3 3/4 inches, 3 3/4 inches. Oops, here we go. Okay, the way I did it, I cut it the same paring knife, in this case 3 3/4 inches, the same thing. So by the way that I've structured my problem, this cut is the same as this cut, or this chord is congruent to the other chord. Okay, well, I seem to think about triangles being really handy things to do, so I'm going to figure out a way I can make some triangles here. Here's the center of my circle. I'll take and make a triangle over here on the left by going with from the center to the side, in other words, a radius. I'll make a triangle with my original chord and 2 radii. Oh wait, they're radii. They must be congruent. They're radii of the same circle. Because I have a handy dandy circle here, and I'm going to do the same thing on the other side. I'll come here, make my triangle with 2 radii. They're radii from the same circle, so they're all congruent to each other. So then what do I have there? Wait. These are the same. These are all the same. Are the triangles congruent? Yes, indeed they are. Side, side, side. Side, side, side. They are congruent by side, side, side. Congruence postulate, I think it was. Okay, well, since they're congruent, yeah, we got that they're congruent. So then, what about this angle right here? That's the central angle on the left and the central angle on the right. I'm thinking those look a whole lot like corresponding angles of congruent triangles. And somehow it seems like I recall from the deep dark past that corresponding parts of congruent triangles are congruent. Yes, indeed they are. These two are congruent. Okay, what does that get us? Well, we're talking about arcs and chords and stuff now. So, look, this angle is on the left is the same as the angle on the right because they're from congruent triangles. They are central angles because they're at the center. So, the arc that they subtend is equal. The arcs that they subtend are equal. This blue arc is equal to this blue arc because they have come from congruent central angles. Everybody see that? Okay. So this arc, what did I start with? I started with green slices, green sticks, my paring knife, and my grapefruit. So I went from an equal cut or an equal sized arc, that the arcs were congruent, and my result was, an equal sized chord. This chord is congruent to this chord. And from that I got that the arc is congruent to the arc. So I went from the chords are congruent to the arcs are congruent. And that just happens to be a theorem for us. 2 minor arcs are congruent if and only if the corresponding chords are congruent. Okay, let's come back to here. What else can I do with this handy dandy cut up grapefruit? Well, I'm wondering how far it is from this chord to the center. I'm going to draw a line, construct a line. That's the shortest distance from the center to the chord. Shortest distance. Shortest distance has to be perpendicular. Another name for this segment in this triangle is it's the altitude, right? It's from the point to the base. And it's perpendicular, and it is the shortest distance. So this is the shortest distance on the left triangle. I'm going to do the same thing on the right triangle. I'll make a line segment that's the shortest distance to the side. Well, I wonder if that's the same as that. I wonder if it's the same distance. So is this chord the same distance from the center as this chord? Well, look at the triangles. I do recall that the left triangle was congruent to the right triangle. And you know, somehow I'm thinking this altitude is the corresponding part of the left triangle to the altitude in the corresponding right, portions of the right triangle. So I'm guessing that corresponding parts of congruent triangles are congruent, and that these two are congruent. Well, I should have marked those with 3, shouldn't I? Those are already marked with 1. Okay, so what do we have then? We started with the distance being the same, the chords being the same, the distance from the center being the same. Okay, so what I started with here was I had congruent triangles, and I know that the chord that's on the outside is equidistant from the center. That gives me that they are, the chords themselves are congruent. Does everybody see that? If it's equidistant from the center, then the length of the chord is the same. Here we have a theorem. That's not exactly a proof, but it gives you a general idea. It's got a few holes in it, but you can get it here from that. So, equidistant chords, if two chords are congruent if and only if they are equidistant from the center. Okay, we'll start with a definition here that I don't think is going to surprise you. The bisector cuts it half in two. Oh wow, what a surprise. Anything that cuts that cuts an arc into 2 equal portions is a bisector. Okay, so a point, a line, a ray, a segment, anything that cuts an arc into 2 equal arcs is an arc bisector. Here's the theorem. Just kind of read through it. Write it down in your cipher. If a chord, the red one, is the perpendicular bisector of another chord, the blue one, then the chord that does the bisecting, red, is a diameter. Let's just kind of get a gut feeling for why this is true. We can prove it with with congruent triangles pretty readily. We've had a lot of practice with that, but let's give a gut reaction to why it's true. I'm going to play with it a little bit. Okay. Bisected means half is above and half is below. So the blue line, a chord, is bisected. Half is above the red, half is below the red. Okay, well look what happens as I slide it along. Because the circle is round, the curvature at the top is the same as the curvature at the bottom. So as I move the bisector, as I slide it, it gets shorter on the top at the same rate as it gets shorter on the bottom. In other words, it stays right in the middle, it stays bisected. Okay? If I put it down here, again, because the circle is round, the curvature at the top takes off at the same rate as the curvature at the bottom as I slide it. And the red stays in the middle. It stays half on top, half on bottom. It stays bisected. Same deal over here. As I slide it, the top gets smaller, the same rate as the bottom gets smaller. Why? Because it's round. The curvature is at the same at the top on the bottom. So as it changes the same. So all along in here, the top stays half of it, the bottom stays half of it. Top half is blue, top blue half is the same as the bottom blue half. The top blue portion is the same as the bottom blue portion. The top blue portion is the same as the bottom blue portion. What I'm getting at here is that all the way along, the top and the bottom are the same, which means the middle is in the middle. Half of it's on top, half of it's on bottom, all the way along. It's always bisected, half on top, half on bottom. That makes the middle. What's the middle of a circle? It's the diameter. So we have our theorem here that if a chord is the perpendicular bisector of another chord, then the chord that does the bisecting is a diameter. Half on top, half on bottom. It's always that way as you slide it along. This is not exactly a converse, but it kind of acts a little bit like one, so go ahead and make note of this one as well. Okay? So that's if the diameter is perpendicular to a chord, then the diameter bisects the chord and its arc. A few things to look at here. Okay, what can you conclude here? I can conclude that AB is a diameter because this is CD is a perpendicular bisector. How about down here? Again, it's perpendicular. AB is perpendicular to CD, and they're equal, 6 and 6. Even though it's not marked as a bisector, it's marked as the same distance. What about this one? Give it a look. Can you say that AB is a diameter? You can. How is that? These two triangles above and below the AB are congruent. Why? Well, they share a side, they have congruent angles, and the other sides are congruent. So that's side, angle, side, side, angle, side. These are congruent. And since corresponding parts of congruent triangles are congruent, the angle here is the same as the angle here. They are a linear pair, therefore they're 90-degree angles. We had a theorem on that. So it is perpendicular. Does it bisect? Yes, it does. You'll recall our theorem with regard to an angle bisector and the opposite side. It does bisect it. So that works here. Here's a few things to practice on if you want to practice. If you look at these, work through a few of them. Go ahead and pause it if you want to work on them, and I'll put the answers up here in just a moment. And here are the answers to make sure you're doing them right. And there's a fun problem here that you might like a little help with, just to help you think back to what you already know. Here we have a garden in which there are 3 bushes. The gardener wants to put a sprinkler in a position so that it waters them all equally. So we'll assume it's a sprinkler that sprays around in a circle, a stream of water that basically lands in a circle on the ground, or that's one that just comes up and makes a circle all at the same time. This should look familiar to you. We have 3 points, and we want it to be on a circle. 3 points on a circle. Sounds like a triangle. They've drawn that down here for you, connected 2 of them. This ought to be looking real familiar here as to what this is. This is a concurrency. It has to do with a triangle. If you connect A and C, what is this point of concurrency? Look, it's the perpendicular bisectors. That's the circumcenter. So this is from last semester. You can see if you make this into a triangle, the concurrency of the perpendicular bisectors will be the circumcenter, which is equidistant from each of the points of the triangle, and that's exactly what you want. You want the water to spray all of them equally. So what you'll have here with the bush then, you'll put the sprinkler about right here, and it will spray in a circle like this around it. So that gets you what you need. And here endeth the lesson.